Hello again. Now we're ready to talk about tangent planes. So let's get a color. Tangent planes. Now uh, as you might have guessed that a tangent plane is a plane. It's a regular plane, and this is one weird thing. Let's go up then. So what is a tangent plane? A tangent plane is just a special plane, as you might have guessed. So let's draw the equation of a plane. So that's going to be a x plus by plus cz equals d. So what are the constants? What are the constants gonna be? So let's get a color to circle our constants. So what are these constants gonna be? What are they gonna be? So let's remind ourselves with let's help visualize this equation of a tangent plane with single variable calculus, and let's see how to do it. So I'm going to draw the x-axis and the y-axis and draw a random function. So this random function wants to be smoother. So the tangent line about this point is going to be of the form y equals mx plus b, and we know what m is going to be. M is just the slope, right? So m is going to be the slope or the derivative of the function. So this the m evaluates to easily to dy dx. And what Alright, and what I was about to say, what is b? So let's leave that for now. So b is just a value of y. Let's remember that b is a value of y, and so a sort of initial value of y kind of thing. So let's say this is just a value of y. Let's call it y0, just a value of y. So we have this y minus y0 equals dy. Let's switch colors. Equals dy dx times x. So is this how it's supposed to be represented? Well, almost. There's still one thing missing, but I think it should be intuitive enough to understand. So at what point is it evaluated? It's going to be evaluated similar to how the y value has an initial value. So let's say the initial value is y sub 0, so we could say, I think it's going to be intuitive that it's going to be the derivative dy dx times the, I guess you can say, the change in x, but it's not really change in x. It's just it's just it's just a variable shifted over a certain amount. I think that's how you're supposed to view it. So this is how you do it in 2 dimensions, or single variable, I guess you can say. So to visualize, let's give this point a value of, let's give this point a value of 2, and this point a value of, I don't know, 10. Could be 10, could be anything. All right, so what you plug into this, where you plug 2 and 10 into this equation is with a neutral color. This y sub 0 would be 10, and x sub 0 is going to be 2. So mm, it's like shifting. It's basically shifting. So hopefully you can understand the intuition behind this. Not gonna do rigorous proofs. I hate those. Well, I sometimes love those, but at times they're very very lazy to do. Okay, so how do you get this this big ass equation to look something similar to this equation? So what we can do is use intuition. So what? So let me draw a graph. Let me draw the x, y, and z axes with this color. Let me draw a straight line. Alright. It's going to be the x-axis, the y-axis, and the z-axis. Now let's say we have a function of, oh no. Let's say we have a function like, oh no. Let me fix some things behind the scenes. Alright. So let's say we have a function that looks something like this. So it would look something like, oops. So something like, oops. Huh. It would look something like this. So how do you get the equation of a tangent plane? Let me draw an example of a tangent plane with the color green. Let's say a tangent plane about this point. I think that is a pretty accurate drawing. So I think that is a pretty accurate drawing. Is it? Is it? I don't think it is. Alright, let me redraw it. Let's say at this point, there we go. I think that's more accurate. So how do we get the equation of a tangent plane? So similar to how we did it in 2 dimensions, in 3 dimensions, it would have to involve derivatives. Well, in this case, it's going to be partial derivatives. So that's nice. So if we were to slice this plane in the slice it slice it in the direction parallel to the x-axis. So let's get a nice color to slice. So it would look something like this. It would look something like this, and the slope would be something like this. Looks like it. Looks like some looks it looks like something like that. So what this definition is that this plane, when you slice it, it means that you got the partial derivative of the function with respect to x. So let me write that in white. So partial f or no, partial z, no, partial z over partial x. Alright, so that's easy. I'm getting too far from my microphone. That's easy. So A, we know A is going to be, since A is encircled already, might as well not encircle it. So A is equal to the partial of the function, always write f, of the function z with respect to x. And that goes the same way for b, which is y. If we were to slice a graph in the direction parallel to the y-axis, it's going to look something like, I don't know what color I should use. Maybe this color, darker color, a darker color. So it might look something like, this, where looks like the slope looks pretty much zero. If you were to view it in the ZY plane, it looks very, very zero. So dy dx is zero. It's zero, but let's generalize it with b being equal, but we know that it's equal to 0, b being equal to the partial of the function with respect to y. And now what's z? To y. Now what's z? Z is basically the function itself. Let's say z is a function of x and y. So z is a big dog. So this c is probably nothing. Could be any other constant. Probably nothing special. So it could be just constant. And d is that was supposed to be drum roll sounds. D, you can say, is the b of z. So remember y mx plus b, y mx plus b. Yeah, this d is the z's b, the z's b, if that makes any sense. So I'm going to label it as, oh no, hold up. I'm going to label it as c sub 0. And we may have successfully transformed a generalized form of the equation of a plane to the equation of a tangent plane. Now we have partial z partial x times some function of x minus x sub 0 partial plus the partial of z with respect to y evaluated at y minus y sub 0. Again, I think the intuition should be enough. It's like a shift. You could say it's like a shift. So now that's all equal to this color z. Well, there's a constant here, but let's assume it's 1 minus c sub 0. that is the equation. Well, I have to be specific here. Well, it's not just partial z partial x. It's going to be partial z partial x evaluated at the points you evaluated at points given. So it's going to be partial z partial x evaluated at x and y, because it could vary depending on the x value and the y value, so we have no guarantee that it has a constant slope. And that also goes the same way for partial z partial y. So all in all, this is the equation of a plane, of a tangent plane, and that kind of looks alright. So let me introduce to you another notation to represent a partial derivative. It's basically a function, and let me draw the more common notation. It's also represented as f sub the function. Let me get this the function and sub x, which is calculated the same way. It's just another notation to represent. Oh no. Again, I was saying that this is another way to represent a partial derivative. So I think I should end it in this panel and give you some applications of the partial derivative of the partial derivative in the future videos. Catch you later.